So we're going to have a look at a topic about the idea of matrices, what they are, how we can use them to solve problems, and there's a whole lot of reasons why matrices are used in mathematics and beyond. One of the key things is that they distill a lot of numerical information in easy packages, which is ideal for computer programs for inputting information, but also it often gets displayed in matrix form. In other words, we're not constrained by algebra and letters, variables, words. We've just got the pure number elements of a problem. And so that's what matrices really are. They're just groups of numerical data which we can then interpret or use to solve particular problems. So really quickly, a few basic ideas, and then we'll go on and look at some more complex matters. So first of all, a matrix, as was said, is a group of numbers usually arranged in rows and columns, and matrices are usually given capital letter names. So in this first part here, we've got the matrix A, and what we have to learn here is that we have something called the order of a matrix, and that's determined by how many rows it has and how many columns it has. So a number of rows, in this case here, there's one row, there's two rows, and there are three columns, 1, 2, 3. So we would call this a 2 by 3 matrix. And that's a really important thing later on, as we'll find out. A 2 by 3 matrix has two rows and three columns. 2 times 3 is 6, which is obviously how many individual elements that there are, and each of these values here would be called an element in the matrix. So we've got the order. Secondly, we can introduce something called the transpose, and we'll use a bit more about the transpose later on, but basically the transpose is when the first row becomes the first column, the second row becomes the second column. In other words, the transpose of a matrix is when row n becomes column n. What usually happens is you find that just everything kind of flips around. So we've got the original matrix A, this first row here, which was 2, 0, 1, flips round. 2 stays anchored at the very beginning, but the 2, 0, 1 becomes 2, 0, 1 on the column instead of a row, and then the second row 1, 3, 3 becomes the second column 1, 3, 3. And in general, if we were to find the transpose of that matrix, we'd end up back to where we started, and that's why we get this kind of little rule here. The transpose of the transpose takes us back to the original matrix. Okay, so the transpose will come into play a little bit later. And thirdly, it's just a little idea of a square matrix. Square matrices are really quite common in mathematical operations. It has n square elements. A square matrix would be something that has effectively the same number of rows and columns. So a square matrix has the same number of rows and columns. It has n squared elements, obviously. So that's just a little definition. So 3 quick things: the order, transpose, and square matrices. Zooming on here, first type of arithmetical operation, addition. We can add the elements in 2 matrices as long as and only when the order of the matrices is the same. So matrix P here has got 2 rows and 3 columns, so that's a 2 by 3 matrix. Matrix Q has 2 rows and 3 columns, so it's a 2 by 3 matrix, and because the order is the same, then we can add them. And the addition couldn't really be much easier. P plus Q is equal to make the point, we add the first element and the first element, and that's your new first element. So let's just write it down. I don't think it's we need to label the point. -1 and 0 becomes our new row 1 column 2 element 0, that becomes -1, and then we've got -2 plus 3 gives us 1. So that's our 3 parts matching up with the individual elements. And we repeat the same thing for row 2. We've got 5 plus 1 is 6, 0 plus 1 is 1, and 1 plus negative 3 is negative 2. So we add the individual elements together, and that gives us our the sum of the matrices P plus Q. And that holds that if we had done Q plus P, we would have got the same answer. In other words, the associative law that we're used to in numerical work holds for matrix work. And just talking very briefly about the transpose, there's an interesting little law at work here that doesn't actually matter whether you transpose first or second when we're adding. If we needed to, we've got our answer there, which was 7. We'll just take that and copy it. Then we'll take it and we'll paste it. So that was PQ. And if the transpose of that, P plus Q transpose, would be 7, negative 1, 1, which is the first row, becomes the first column. And at 6, 1, negative 2, which was the second row, becomes the second column. So that's P plus Q transposed. However, if we had actually transposed the two matrices first of all, I would have got 3, negative 1, negative 2, 5, 0, 1, and Q is 4, 0, 3, 1, 1, negative 3. And if we add those two together, you can see that we would still get the same answer of 7, 6, negative 1, 1, and 1, negative 2. And that's because the addition process is very straightforward. We're linking up the same matching places, so it doesn't matter whether we add them and then transpose the sum, or whether we transpose them first and then add, you get to the same place in the end. So interesting little properties of adding matrices. And the last point just for this little video, there's lots of wee bits and pieces that we're covering first of all. Multiplying matrices by a scalar. So as far as usually concerned, a number, whether greater than 1 or less than 1, whatever you multiply by, you can multiply individual elements. You may have had experience of that if you've ever worked on, for instance, the unit vector idea that you might have come across. Just to make it the idea, you might have come across a vector as being something like that, where you've got a fraction and a matrix. Remember, a vector quantity there is really just written in matrix form, and you know then that we could write it like that, which is a matrix times a scalar, or we could just work out the individual values divided by 5. So you probably already get the idea that if you're multiplying a vector quantity, if you're doubling it or halving it, we can just apply that calculation to each individual element, which allows me to actually work out this interesting matrix equation. So we've got a matrix X such that 4x minus some matrix 3, 1, 4, 7 gives us an answer of 5, 3, 0, 13. And we can use our basic vector arithmetic to solve this. What we would want to do first of all is isolate the 4x term on the left. In other words, that we want to negate this vector subtraction, which we can do effectively by adding the vector back on, and they will cancel out, as long as then I'm adding the same vector on the other side. Okay, so we can add the vectors on. Effectively then we're saying that 4x is equal to 5, 3, 0, 13 plus 3, 1, 4, 7. Okay, so we're adding the vectors onto both sides, and we end up with this addition to do where we can bring together the elements. It's two square matrices. Square matrices are great to work with because the order is always the same. If you're all 2 by 2 matrices, you don't have to worry about it not adding or subtracting or even multiplying, as we'll find out later on. So we've got 5 and 3 makes 8 as our first element, 3 and 1 makes 4 on the bottom row, 0 and 4 makes 4, 13 and 7 makes 20. And so we have the equation 4x equals 8, 4, 4, 20. And in order to get x on its own, we need to divide by 4, or another way would be to represent that as a quarter. That's the best way to, we don't usually put a fraction, a matrix in a fraction, but we would multiply it, instead of putting a line over 4, multiply it by a quarter, and then we can multiply in, if it's appropriate. If the elements are not multiples of the fraction, you can leave it in that form. But if I can divide everything by 4, then I will. And that gives me my answer that the vector x is 2, 1, 1, 5. Solving a vector equation using just basic standard algebra techniques and our addition and scalar multiplication of matrices. There we go. Nice wee introduction to matrices. We're going to go on in the other examples and actually do things that are a wee bit more interesting. But you've got to know the basics before we can hit that. Okay.